We've all probably wondered at one point in time, what causes our mirrors and glasses to work? The answer to these questions lies in the science of mirrors and lenses, which we will teach you about today. We will first begin with some basic diagrams of reflection and refraction. We'll first begin with our basic reflection diagram. In a reflection, we have our mirror, a light wave being emitted toward the mirror known as the incident ray, and the same light wave bouncing off the mirror known as the reflected ray. At the point where the incident ray strikes the mirror, a perpendicular line can be drawn, known as the normal line. This line creates two separate angles, known as the angle of incidence and the angle of reflection. This diagram displays a very important concept about reflection, known as the law of reflection, which states that all components of reflection are in the same plane, and that when light reflects off of a mirror, the angle of incidence is always equal to the angle of reflection. Next, we'll talk about refraction diagrams. Refraction, or the bending of a light wave, occurs when the light wave crosses a boundary into a new medium. In this diagram, for example, we have a boundary between air and glass. Approaching the boundary, we have an initial light ray, known as the incident ray, that upon passing the boundary changes direction and is now known as a refracted ray. Once again, at the point of incidence, a perpendicular normal line can be drawn, which creates an angle of incidence and an angle of refraction. Some key points to note in a refraction diagram are that the angle of incidence and the angle of refraction are never equal, and that the amount of refraction toward the normal line depends on the optical density of the medium, indicated through a value called the index of refraction. A denser medium will have a higher index of refraction, resulting in an increased refraction of a light ray. For example, glass, which is denser than water, will cause greater light refraction. So now let's move on to talk about plane mirrors and convex lenses. Let's go first into some basics about plane mirrors. A plane mirror is a flat reflective surface, usually comprised of metal covered in a sheet of glass. In this example, we have a plane mirror and a light source, in which light is emitted from the source and is reflected off the mirror to be perceived by a human eye. It is important to note that with the perpendicular normal line, the angle of incidence is equal to the angle of reflection. The human eye perceived the light source as behind the mirror, which created what is known as a virtual image. The characteristics of an image formed by a plane mirror include that the image is behind the mirror or virtual, upright, the same size as the object, and also the same distance from the mirror. Now let's move on to convex lenses. Some key points about convex lenses include that the lens bulges outward facing the incident rays, refracted rays converge to a single point, and if lenses are more curved, the rays are more refracted. It is crucial to note that the image characteristics of a convex lens, such as orientation, location, magnification, and type, vary depending on an object's distance from the lens. Here's a diagram showing the 5 possible positions of an object that light bounces off of. Each yields its own image type, and we will learn 3 of these scenarios. A great way to demonstrate these scenarios of how a convex lens refracts light and creates an image is by using a ray diagram. Before we look at the 3 scenarios, let's label the basic parts of a simple ray diagram, which allows us to predict image orientation, location, magnification, and type. On the diagram, F represents the focal point. This is the principal axis. Here's the object in which light bounces off of. The blue lines represent incident rays, which travel towards the lens where they are refracted and are now referred to as refracted rays, which are represented by red lines. The point at which the rays converge is where the resulting image is formed. In summary, here we have light bouncing off of an object referred to as incident rays, which refract through the convex lens and become refracted rays that converge and produce a single image. The incident ray that is parallel to the principal axis is refracted to go through the focal point. The The incident ray that goes through the center of the lens is not refracted. The incident ray that goes through the focal point is refracted to be parallel to the principal axis. Like we stated earlier, the resulting image varies depending on the object's distance from the lens, and we will show you 3 different scenarios. So let's start with our first scenario, where the object's distance from the lens is greater than 2f. Here is a diagram depicting the scenario with the object, incident rays, refracted rays, and image all labeled. When the object distance from the lens is greater than 2f, the image is real, inverted, and reduced in magnification. Now let's move on to our second scenario, where the object distance is between 2f and f. Once again, the ray diagram is labeled with object, incident rays, refracted rays, and the resulting image. In this scenario, the image is real, inverted, and enlarged in magnification. In our third scenario, which is a bit more complicated, the object distance from the lens is less than the focal point. Here we have another diagram where we once again have our object, our incident rays, and our refracted rays, but this time we have virtual rays and a virtual image. So why is the image formation in this scenario different from the rest? Well, this is due to the fact that real images are formed by the intersection of refracted rays, known as converging rays, but in this scenario, as you can see, the refracted rays actually don't converge. But because we know that light travels in straight lines, we can actually trace back to the point where the rays actually diverge from, which is the point where the virtual image is created. So in this scenario, the image is virtual, upright, and enlarged in magnification. Now let's learn about the helpful thin lens equation. The thin lens equation is a useful way to demonstrate a relationship between an object's distance from the lens, focal length, and image distance from the lens. Here's the diagram that displays all 3 of these variables, and here's the actual thin lens equation. The inverse of the object distance plus the inverse of the image distance is equal to the inverse of the focal length. So as long as you know 2 of the variables, you can find the third. Now that we know the equation, let's move on to an example problem. Calculate the distance of the image generated from the lens if a penguin is 20 meters from the lens and the lens is convex with a focal length of 5 meters. So take a minute to figure out how we'd solve this problem and also check out the penguin. Let's now move on to the solution. Before solving, let's first demonstrate what exactly is going on by drawing a diagram. We're given the focal length and object distance, and we need to find the image distance. Now we can use the thin lens equation. The inverse of the object distance plus the inverse of the image distance is equal to the focal length. Plugging in the values, you get the following. And with a little algebra, your answer will be 20 over 3 or 6.667 meters. Lastly, let's talk about a unique application of mirrors, which is the coiled optic fiber. Optic fibers are created by drawing out extremely pure glass into long strands, which can be as thin as 9 microns in diameter. The glass is then coated with layers of plastic called cladding, which creates a mirror around the glass and a medium for the light. The mirror exhibits what is known as total internal reflection, which means that the light waves, usually infrared light, continue to bounce along without leaving the fiber. Let's go into greater detail of how exactly light travels through a coiled optic fiber. Here's a picture of an optic fiber that we'll label together. Here we have light traveling through an optic fiber with air on the outside. And as it travels, it bounces off the glass or cladding. As you can see, while the light ray travels through the optic fiber, it is unable to escape and exhibits total internal reflection. Through this process, optic fibers can virtually bend light to reach a desired destination. So why exactly do optic fibers even matter? Well, optic fibers are able to transmit data through a series of laser pulses, in which one laser switched on and off equals one bit of data. These different bits can then be combined in millions of different combinations to in turn form a bigger picture. This can occur up to several billion times per second, which allows for a large amount of data to travel long distances. For this reason, optic fibers are very suitable and useful for long distance communication and transfer that we use on a daily basis.
Wow!
Such as email, landline telephones, and cable televisions. Optic fibers are so widely used for long-distance communication in our world today because they are faster in distance transfer and are more cost-effective than traditional copper wires. So that's all we have about mirrors and lenses today. We hope that next time you pick up a mirror or look through your glasses, you have more of an idea of what exactly is going on.